video. So we're going to be discussing section 3.1 today, which is our introduction to curve sketching, or which the book calls it the first derivative test is the name of the section. So in chapter 2 we had spent a lot of time discussing derivatives, what they are, kind of some applications of them, and now this chapter is really getting into more of the application. Like, here's what we can do with our derivatives, right? So let's take a curve. Right, and let's say that, or even just take a graph in general, or function, and I want to be able to study it, right? Now, we don't want to have to bother with kind of plotting all the different points and trying to make it perfect, because with our human nature kind of drawing things, it's not going to be perfect. It's always going to be off a little bit. So what do we do in that case? Well, instead of getting specific points, we can have an idea of a couple of significant points that will guide the rest of our graph, right? 2, 3, 4, maybe more, that give us an idea of where the big changes in the graph happen, and then know that everything else kind of has a general direction in that. So here we're presented with a graph. And the two significant points that I kind of note on this graph is at the top peak here and at the lower peak here. Now, why do I say that? Well, that's because at these points is where my graph is kind of starting to do something different. So on the left, it was moving up, 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 until it hits a point. But now it's going down. So it's going down, down, until it hits this point. And at this point, it starts to go back up again. Right? So if I were able to somehow figure out what these points were and what exactly was happening on each side, then I would be able to figure out what the graph's doing in general, at least with some more simple polynomials. And so that's really what section 3.1 is going to be all about. Now, at these points, right, the key to this section is to notice, let's think about what the slope is doing at these points. So I might grab a different color, highlight this. So we have, let's see, that one was out. It's unfortunate. Not sure if this will be clear enough here, but I'll try to mark it on the picture. So here's a tangent line to my graph at this given point. We've talked about tangent lines, finding the slope above a tangent line at a given point. We have this tangent line that's falling right alongside the curve. And so we can get an idea of where the curve's going at these points, right? Something I want to make note of is what's happening to the tangent lines at the 2 points, that things change at, right? Because we noticed beforehand, right, that the lines are kind of tending upwards, and afterwards the lines are tending downwards. So there's somewhere in the middle, which is at that point, where the tangent line is flat. And the same thing will happen here. We have a flat sort of tangent line. Now these are horizontal lines, and we are familiar with horizontal lines. These have a slope of 0, right? Traditionally, we would see them as y equals 4, maybe y equals -3. Those are kind of the equation of horizontal line, right? Now, we like our slope-intercept form, y equals mx plus b, but there's no mx here. It's just the b part. And that's because it only intersects at b, right? There's no slope, there's no change. So that's kind of our goal here, right? We want to see these points where we have that kind of special line, because everything else is going to tend in a similar direction after that point. So with that all being said, let's go ahead and take some time and move into some examples. example number 1. Okay, let's say that I have the graph x squared, so y equals x squared minus 2x plus 4. Okay? And I wanted to sketch this graph, but I need to have a knowledge of maybe where those changing points are, what we're going to call extreme values, or kind of referencing back to the graph we had real quick. Notice that these are, in a way, they're sort of a relative maximum and relative minimum. Clearly the left side keeps going down, right? And the right side keeps going up. But at these points we find sort of a maximum within the general region. And at this point we find a kind of a general minimum. Okay? So we want to be able to find where those points happen. And we call those points, they're called critical points, right? And the way we find critical points is, again, by looking at that horizontal, those spots where I have a horizontal tangent line, right? Now, in order to figure out where I have a horizontal tangent line, I have to figure out where the slope of my function is equal to 0. Well, how do I get the slope of a function that's not a line? Well, that's where the derivative comes in, right? So I'm going to take my function, and I'm going to take the derivative of both sides. So I'm going to get dy over dx. And then from the last chapter, we know that the derivative of x squared is going to be 2 times x. The derivative of negative 2x is going to be minus 2. And the derivative of 4 will be 0. Okay? So I get dy over dx is 2x minus 2. Now, as I said, this most significant point is when it's going to be 0. So I want to take my derivative and want to set it equal to 0. So what do we find when we do that? Well, I'm going to end up with 2x equals 2, which means that x is equal to the number 1. Okay? So, here's a clear example of, this is the x point where the slope of this graph is going to be 0, right? And what we would see typically, we talked about before, this is actually the vertex, going to be the vertex of my parabola, right? Because the parabola always has a point where it, where the bottom's at and everything else comes up from it or comes down from it. That's going to be what this point is. We can find that specifically in our graph, right? If I want to find, so this is called the critical value, just like that. So if I want to find the critical point, in this case, I'm going to plug that into my function. So if I call this f of x, right, y equals f of x, then my point is going to be 1, and f of 1. So 1, clear here, f of 1 is going to be 1 minus 2, which is minus 1, minus 1 plus 4 is 3. So the point ends up being 1, 3. Okay? So at 1, 3, we have a critical point. Okay, that's where something special is happening. We don't know what exactly it is yet, but that's why we're going to put in the work here to see what's going on. So, with all that being said, let's take a look at what's happening maybe to the left and the right side of this critical value, right? So 1 is my special point. I'm going to put this onto a number line. 1 is my special point. And now what I'm going to do is I'm going to look at what's happening to the slope when I'm on the left side of this graph, and when I'm on the left side of this line, and whenever I'm on the right side of this line. Okay? And this whole process down here that I'm about to do is exactly the first derivative test. Good. So, how do we do the first derivative test? Well, I'm about to walk us through it. So here's our real line, right? I put the number 1 on here because that's a critical value. And now I'm going to see what's happening on the left and the right side of this picture. So, let's take a number, say 0. I'm going to write on the left side of 1 and plug it into the derivative, right? What happens when I put 0 into the derivative? Well, I'm going to get 2 times 0 minus 2, which is minus 2, which is less than 0. So it's negative, right? What does that mean? Well, that implies that everything to the left of negative 1 has a negative slope, which means that my graph is going downwards. It's decreasing. If I plug in a number to the right of 1, say 2, right? 2 times 2 is 4. 4 minus 2 is 2, and that's positive, right? And so that has the opposite effect. That means all my tangent lines have a positive slope, so my graph is actually going up. Alright? So, we can actually use the information we have now to make a complete graph. We know what's happening, we know kind of what our graph is going to do. Okay? Good. Now, what we can also see, right, is notice that before 1, we're going down. And after 1, we're going up. That means that, so maybe I'll go ahead and try to put this on a graph, right? So we know we have the point 1, 3, right, which would be about here. And we know that before 1, I'm going down, and after 1, I'm going up. So our graph might look something like that. What does that tell us about 1? Well, in this case, it's a minimum. It's a minimum point, right? We can clearly see that because that's kind of the lower end, right? And that's generally what's going to happen, right? If I decrease before a point and increase after, that means I'm going down and then I'm coming back up. So that means that that is a minimum or a relative min in that case. If we have the opposite case, which we'll see in another example in a sec, what's going to happen is you're going to have an increasing first and then a decreasing, right? So that means that I was going up to a tippy top and now I'm coming back down. And so that's a maximum or a relative max in that case. Okay? So let's go ahead and go through another example where we're going to have something of that sort. So let's step up our polynomial a little bit. We'll do f of x is going to be x cubed minus 6x squared plus 9x plus, I don't even need to put a number on it. We'll just call it that. Okay? So, going off the logic of the last problem, right? If I want to graph this, first I'm going to take the derivative, right? Which I'll write in this case is f prime of x. This is going to be, the derivative is going to be 3x squared, 6 times 2 minus 12x, derivative of 9x is plus 9. Now, I want to take this thing and set it equal to 0. Again, because we want to see where our critical points are at, right? So, this is a quadratic. So when we're dealing with quadratics, we have a few ways to solve them, right? But the easiest one would be if we could take this and factor it. Well, is there anything that the three terms have in common? 3, 12, 9, they're all divisible by 3, right? So let's take a 3 and pull it out. So we're going to get x squared. 3 times what gives me 12? Well, that's 4. And 3 times 3 gives me 9. And so we get this. So I just rewrote my expression. It's the same thing, but I factored a 3 out. Okay? This polynomial, we also can actually factor further, right? What needs to happen is I want two numbers that multiply to give me positive 3, but add up to give me negative 4. So, if I want that, the only numbers that multiply to give me 3, right, are 1 and 3, right? And we definitely don't want positive 1 and positive 3, because that would give me positive 4. So instead, we're going to want minus 1 and minus 3. Okay? So we get 3 times x minus 1 times x minus 3 is equal to 0. Okay? So then we just take each individual term and set it equal to 0. And that'll give us our critical values, right? So we're going to get x minus 1 equals 0 and x minus 3 equals 0. Clearly 3 can't be 0, so we won't include that one. From here, we're going to get x is 1 and x is 3. So these are my critical values. Okay? To find my critical points, I'm going to plug them into the function. So when I plug 1 inside my function, I'm going to get 1 minus 6. 1 minus 6 is negative 5, and negative 5 plus 9 gives me 4. So we have the point 1, 4, and we have, so I take 3 and plug it in into the function. We're going to get 3 cubed, which is 27. 27 minus 54, negative 27, and negative 27 plus 9 times 3, well, that'll also be 27, so that actually ends up being 0. So, that was actually a nice little computation there. So we have 2 points, 1, 4, and 3, 0, and these are our critical points. But of course, we need to figure out if they're maxes or mins, right? So, I'm going to create my number line. Right, so maybe I'll put move this down a little. And we're going to have 1 and 3 here. And to the left of 1, right, we're going to take numbers to the left of 1 and plug them into my first derivative. Now, you can feel free to plug it into as it is up here, right, and see what the values are. Or we could actually just take it and plug it into this factored form, right? Because these are still equal to the derivative, right? And so that's going to make my calculations actually a bit easier, right? So let me kind of show that work explicitly as we're going through, okay? So first, I'm going to take 0 and I'm going to plug it in. So if I plug in 0, I'm going to get 3 times 0 minus 1 times 0 minus 3. Okay, so what are we going to see here? We see that 3 is a positive number, negative 1 is negative, right? And negative 3 is also negative, right? So we have a positive times a negative, which gives me a positive. So, and you could calculate this out explicitly, it would actually be 9, but it's going to be positive. It's going to be a positive number, right? So, to the left of 1, I'm increasing. I'm going upwards, right? Next, what I need to do is I'll plug in a number between 1 and 3. So 2 would be the next choice. So then we're going to get 3, 2 minus 1 times 2 minus 3, right? Just plugging it into the first derivative. So what are we going to see here? We have positive 3, 2 minus 1 is positive, 2 minus 3 is negative. So overall we get a negative number. Now again, if you want to calculate that, by all means, go ahead. You're going to get, I think that's negative 3. So that's clearly negative. So in this region, we're negative, so we are decreasing. Finally, let's plug in a number after 3. We'll do 4, right? So when I plug in 4, I'm going to have 3 times 4 minus 1 times 4 minus 3. Again, feel free to calculate if you'd like. This actually ends up being 9. But we can also see 3 is positive, 4 minus 1 is positive, and 4 minus 3 is positive. So the whole calculation should be positive, right? So after 3, I'm increasing. Okay? So now what do we see here? Let me kind of move some of the calculations out. Okay? We're increasing before 1 and decreasing after 1. What does that mean? Well, that means 1, 4 is a relative maximum. Right? Because that's a point where there's an increase before and a decrease after. That's what we mean by a relative maximum. Okay? So, and then at 3, 0, what's happening is we have a decrease beforehand and we have an increase afterwards. Right? So, that's a relative minimum, right? Because we're decreasing before and increasing afterwards. Apologies for the laughter. There is other people in the room currently, so it's a little hard to maintain at times. Anyway, we'll keep going here. So, 3, 0 is a relative minimum point. Good. Now, what is that going to tell us about our graph? Well, we're going to learn in 3.2 that there's maybe more we could do if we wanted to, but as for now, let's just go ahead and give a good sketch of what this might look like, right? So we have 2 points. We have the point 1, 4, and we have the point 3, 0. So about here, right? And we know before 1, 4, we are increasing. So we're doing something like this. After 1, 4, we're decreasing. And before 3, 0 as well. And then after 3, 0, we are increasing. So it looks just like that, right? We want to make sure to make clear that 1, 4 is a relative maximum point, right? We're increasing and decreasing afterwards. And that 3, 0 is a relative minimum point. So we're decreasing and then increasing with that one. Okay? So, there you go. These are our critical points. And kind of, this is the first derivative test right here. So, yeah, again, reiterating first derivative test. This is the first derivative test right here. Okay? To kind of figure out what those critical points are. Good. Okay. So, a couple of nuances with this. I'll mention them both here just real quick. Number one. The first thing to consider is we might have graphs or might have graphs that have critical points that may not be a relative max or min. Okay? Case in point, x cubed, just by itself. Okay? What happens when I take the derivative of x cubed? Well, I get 3x squared. And when I set that equal to 0, there's only one option, right? And that's x is 0. Great. However, and you could plug that into the function, so our critical point in that case would be 0, 0. However, when I do the first derivative test, right, if I plug in a number before 0, we get like -1, right? We get 3 times -1 squared. Well, that's positive, right? So we're increasing. But if I plug in a number after 0, like 1 for example, we get 3 times 1 squared. That's positive, right? We're still increasing. So before 0 and after 0, apologies again, before 0 and after 0, we're increasing in both cases, right? So 0 is neither a relative max nor a relative min, right? So if you're sketching a graph of this function, we cannot, I repeat this, we cannot be increasing and then say, okay, well, there may be 3 significant points and try to dip down or something and then increase, right? Because you're creating something that's not there. The graph of x cubed should always be increasing. It might slow down around 0, but that doesn't mean it starts decreasing or anything, okay? So please keep that in mind. If it's not indicated here that the point is a relative max or a relative min, do not draw it as such, okay? Just kind of pass through it on the way. Just acknowledging what you're doing on the left and on the right. Okay, I won't be a stickler on how perfect you make that critical point look. Okay, second. Critical values can also come in a second form. And that is that they may not necessarily always be values that make the derivative 0. But they could also, so I'll write this, critical values come also when f prime of x, or I'll write dy over dx, are undefined. Okay? So, here's a good example. Let's talk about f of x is 1 over x squared as a function, right? when we take the derivative of this, and you should be able to remember some of your derivative rules, right? We want to rewrite this as x to the negative second power. So then f prime of x is going to be negative 2 over x cubed, right? If we try to set this equal to 0, we're going to have a problem, right? There's not going to be anything that makes this 0, right? And if I put, right, I can't make the denominator equal to 0, right? Because that's bad, right? And 2 can't be 0, so this isn't going to work. However, I still have one critical value, which is x equals 0. And that's because it does make the denominator 0, right? And breaks it. So there's kind of still a significant point on the graph in terms of that it kind of breaks your derivative down a little bit, right? So it's still worth studying, right? And the reason why I picked this example out in specific is because if I still include 0 on my number line, right? Keeping in mind I can't plug it in, but I can plug in any other number around it, right? Let's plug in 1, negative 1 in here, right? If I plug in negative 1, negative 1 cubed is negative 1, and negative 2 divided by negative 1 is positive 2, right? So on the left side, we're positive. So we are increasing. On the right side of the graph, if I plug in 1, for example, I get negative 2 over 1, which is negative, right? So I'm decreasing, right? So it was still worthy to consider that point because I'm increasing before it and decreasing after it. But that's not, I can't plug in 0 into my function or even into my derivative and get a value out of it, right? And there may be times where you can plug, it may not work in the derivative, but it may work in the function. But still, there's some sort of action there that's kind of breaking down your graph. And so it's why we need to still split up, use those values as critical values, right? And if we were to look at the graph of this function, we would see that it would look like this, right? That the graph is increasing on this side, decreasing on this side. 0 is still a critical value, but not because it gives us a horizontal tangent line, but because I can't have a value at that point. So, just another example, if you ever have a function like that, to keep in mind that your critical values could also come from making the denominators. Good. Okay. Well, that's section 3.1. Thank you all for watching. Look forward to my next video, which I'll be recording here in a little bit. So, see you all in the next one.